let's cover one section from chapter 4 on Borel sets. The title of chapter 1, open sets, closed sets, and Borel sets. I'm taking your knowledge of open sets and closed sets to be extensive, and we had some background material to refresh your memory on open and closed sets. But let's look at probably something you haven't been exposed to before, the idea of Borel sets. So let's recall in part some of the behaviors of open sets and closed sets in terms of unions and intersections. We had, well, for one thing, we had classified a set of real numbers. Can't emphasize this enough, and it's pertinent to the conversation about Borel sets. A set of real numbers is open if and only if it's a countable disjoint union of open intervals. So open intervals are very fundamental in determining open sets of real numbers. They form the base for the usual topology on the real numbers. If you take a topology class, you may hear something like that said. Open sets are made out of open intervals. Open sets of real numbers are made out of open intervals. Okay, and we had a couple other properties. We had that a countable union of open sets is open and a countable intersection of closed sets is closed. Actually, we had an arbitrary union of open sets is open and an arbitrary intersection of closed sets is closed. But for this section, I want to draw particular attention to the concept of a countable collection of sets. And here's why. We're trying to set up integration. So we're going to have to add up some stuff. Like you had Riemann sums, we'll have something. The book never uses this terminology, but we'll have Lebesgue sums. And it doesn't make sense to add up an uncountable number of things. Well, arguably, that's what an integral is, but we're trying to develop integration. So what we'll need to do is do some summation, and it does make sense to sum a countable number of things. You treat it as a limit of the partial sums of the associated series. So you sum countable numbers of things in calculus too. They're called series. So because we're working on developing some stuff related to summations, that's the reason we've taken this fascination with countable this and countable that at this stage. Okay, but these I'm taking as motivational principles. Open set of real numbers if and only if countable, there it is, countable disjoint union of open intervals. Countable unions of open sets are open, countable intersections of closed sets are closed. We're going to talk about collections of sets and look at countable unions and countable intersections of within those collections. First, not our big definition of this section, but the first step in that direction. A collection A of subsets of a set X is an algebra, also called a Boolean algebra, but we'll stick to the term algebra. It's not really algebras per se that we're interested in, but particular kinds of algebras. It's called an algebra of sets if whenever A and B are elements of that collection of subsets, then A union B is a collection of that subsets. Whenever A is in that collection of subsets, then A complement, the little tilde, is being used to indicate the complement of A. A complement, that is X set minus A. This is the notation used by Royden for set subtraction. The complement of A is also in this collection of subsets. And if A and B are in the collection of subsets, then their intersection is. First off, this third property is redundant. De Morgan's laws would tell us, hey, if this collection of sets is closed under unions and complements, then it's closed under intersections. So let's go ahead and list all three steps, and they are respectively closure under finite unions. I mean, I could do some induction stuff and show if it's closed under union of two, then it's closed under finite unions. I can show that by induction. That doesn't mean it's closed under countable unions. That's a different structure. But this first condition says this collection of sets A is closed under finite unions, complements, and part three, finite intersections. So we're taking subsets of a given set X. For us, set X will be the real numbers, and we'll be considering subsets of the set of real numbers. And we'll look for closures under these three ideas. A little addition to the fourth edition of the book is we're also going to require that the empty set and X itself be an element of this collection of subsets of X. This avoids having an empty algebra. It just cleans things up a little bit. I'm not interested in empty algebras. I'm interested in ultimately in some pretty big algebras of sets. Some examples, for an example of an algebra of sets would be, let's take set X to be the natural numbers. We can take A to be the empty set, the natural numbers, the collection, the set of even numbers, even natural numbers, and the set of odd natural numbers. That's closed under unions, that's closed under intersections, and that's closed under complements. So there's an example of an algebra, an uninteresting example maybe, but there's an example of an algebra. As I commented, instead of talking about intersections and unions of pairs, we could talk about intersections and unions of any finite collection. Induction will allow us to show that. Theorem 1.4.a says, given any collection C of subsets of X, there is a smallest algebra A which contains C. That is, if B is any algebra containing C, then B contains A. Smallest is a misleading term maybe. It's not smallest in cardinality, it's smallest in set inclusion, an idea of set inclusion. Specifically what's said here, an idea of set inclusion contains. So a collection of sets A is a subset of collection of sets B. That's what these last few symbols in the statement mean. And let's go through proof of that. Okay, so some supplemental notes. All right, so claim is given any bunch of subsets, call it C, of a given set X, there's a smallest algebra which contains all of those sets in that collection. All right, let's let calligraphy F be the family of all algebras B of X that contain C. Okay, the argument here is actually, it's fairly elementary. It's not necessarily easy, but it is a fairly elementary argument. These sets are going to fly around quite a bit. They use the word family and collection, and all these things are sets of sets in some cases. But we're letting F be the family of all algebras that contain this collection of sets C, algebras on set X. So what that means is F contains all of the collections of sets which contain this collection of sets and which is closed under unions, intersections, and complements. Finite unions, finite intersections, and complements. Is this collection F? Is there anything in it? Yeah, take the power set of set X, sometimes denoted 2 to the X. We saw notation related to cardinality about that. Take the power set of X, that by the axioms of set theory, the power set of every given set exists. So the power set of set X exists. That includes all subsets of X. So it includes this collection of subsets in this collection C as well. So this collection, this family F is not empty. And what we're going to do is define the intersection of all algebras in this family and call that A. And we're going to establish that A is two things. It is an algebra and it's the smallest algebra. To establish the algebra part, we need those 3 principles. So we only need 2 of them if you want to use De Morgan. And then the smallest thing, we'll look at the that is statement to establish the smallest and elaborate on that. Okay, so first we're defining A to be an intersection of all of these collections of subsets of X. All right, so A itself is a collection of subsets of set X. C, those collection of sets, they're subsets of all of the algebras in family F, because family F is the set of all algebras that contain this collection of sets. So certainly C is in all of the B's, which are in family F. So when you intersect them all up, hey, if C is in all such B's, when you intersect all these B's up, C is in the intersection as well. C is a subset of the collection of sets A. So A contains C, and that was part of it. A contains C. Now about the algebra part, suppose A and B are elements of this thing we've defined up here. We're trying to show calligraphy A is an algebra now. So first, let's show it's closed under unions. Take A and B to be elements of calligraphy A. That means A and B are elements of all algebras in family F, because A consists of the intersection of all algebras in family F. So if set A is in collection A, then it's in all of these B's, and hence it's in this intersection of all of these B's. And similarly for set B. So A and B are both in all of the calligraphy B's in family F. So their union is in all of those calligraphy B's, because those calligraphy B's are themselves algebras, and algebras are closed under unions. So A and B coming out of collection A are in all of these B's. Since the B's are algebras, then the union set A, union set B, must be in each of the B's, and therefore must be in the intersection of those B's. That is, if A and B are in calligraphy A, then A union B is in calligraphy A, and calligraphy A is closed under finite unions. You want to do intersections, be the same thing. Complements are the same thing. Similarly, if we take an element of calligraphy A, then that element A is in all of the B's. The B's are closed under complements because they're algebras. So the complement of set A, X set minus A, there's my preferred font for that, X set minus A, / set minus in LaTeX. The complement of set A is in B for all of these B's in that family, because each of those B's is itself an algebra. So we've got A complement in all of the B's, then A complement is in the intersection of those B's, and that means A complement, set A complement is in calligraphy A, the collection of sets. So we've got A closed under complements. We don't have to show closure under intersections, though it would be quite similar to what we showed up here for unions. We can use De Morgan to get that. So taking advantage of De Morgan's law, we don't have to show that we have closures under intersections, though if you want to, it's straightforward from this. So we've got A closed under complements, closed under unions, closed under intersections by De Morgan, and containing C. All right, then A, calligraphy A, is an algebra which contains a collection of sets C. Part 1 contains C. Part 2, closed under unions. Part 3, closed under complements. Part 3A, closed under intersections by De Morgan. It's an algebra and it contains collection of sets C. Now about this smallest thing, this is going to happen pretty fast, but the ideas really aren't that involved. It's hard to follow maybe all of the letters and stuff. But the claim is if B is any algebra containing C, then B also contains collection of sets A. That's what they mean by smallest. You take any algebra that contains C, it also contains A. There's no collection of sets, quote unquote, smaller than A. They're all bigger than or equal to A in some sense, in a set inclusion sense, to be precise, as we'll spell out right here. So if B is any algebra containing the collection of sets, then it's in that collection F. So it's one of these in this intersection. Well, hey, A is the intersection of all of these things. So certainly calligraphy A is a subset of any particular one of these. A is a subset of any particular one of those B's in that collection, that family F. So B contains A, or A is a subset of B. In that sense, A is the smallest algebra containing collection C. So this is rather a constructive proof because you claim the existence of a smallest algebra containing this collection of sets C, and you actually, in some sense, constructed it. You took the intersection of all the algebras containing that collection of sets and showed that thing is itself an algebra, and that thing itself contains C. So there's how we constructed algebra A, which is claimed to exist. We've established it has the appropriate properties. All right, I claim that was an elementary proof. You might want to pause the video and read through it a couple of times to try to make sense out of all the words in the set theory. Since there is a unique algebra containing some collection of sets C, let's give it a name. The smallest algebra C, that is this algebra we were talking about in theorem 1.4.a, where C is a collection of subsets of X, is called the algebra generated by that collection of sets. All right. Set X, for us, will be the real numbers. A collection of subsets of set X that we're interested in, one of these kinds of C's, a collection of subsets of the reals, open sets, maybe even open intervals. So what we'll do is we'll take the real numbers to be set X, a collection of sets we will be interested in are the open sets. And we'll be interested in something like an algebra generated by the open sets. It's a little more involved than simply an algebra. We were constrained up there, as was observed at the top of this page, with closure with respect to finite collections. I'm kind of wanting to do some analysis stuff here and do something infinite, but I want to do some summation too. So instead of jumping to arbitrary infinite, we're going to look at, as I warned you, countable. So what we want to do is take the idea of an algebra and extend it from closure with respect to finite unions and intersections to closure with respect to countable unions and intersections. And such a thing is called a sigma algebra. An algebra, calligraphy A, of sets is a sigma algebra, or a Borel field. I prefer the term sigma algebra. I will almost exclusively use the term sigma algebra, as will Royden and Fitzpatrick. An algebra is called a sigma algebra if every union of a countable collection of sets of A is again in A. In other words, calligraphy A is closed under countable unions. Oh, then De Morgan's going to tell you it's closed under countable intersections as well. We don't have to show that. De Morgan gives us that. This collection is closed under complements, right? Right, you were told it was an algebra. So what we've really added is not only closed under finite unions, but also closed under countable unions. And implied from that, closed under countable intersections as well. So a sigma algebra is a collection of sets closed under countable unions, countable intersections, and complements. You don't need to show all three of those because of De Morgan to show a collection of sets is an algebra. An example of an algebra that's not a sigma algebra is the following. Let's take X to be the real numbers. Consider all subsets of the real numbers, call it A, such that either A is finite or the complement of A is finite. So some examples of such sets are, well, all finite sets, not all infinite sets, because the complement of an infinite set could be infinite itself. So I need to be careful with the other part, but certainly all finite sets are in this collection. Give me an example of an infinite set that's in this collection. How about all real numbers except 4? That's complement, certainly finite because its complement only consists of 4. And really, I can't get much more creative than that. Examples of the other kinds of sets where the complement is finite. They're complements of finite sets and finite sets. That's what's in A. This is an algebra because if I union together, and let's check it for unions to see if it's an algebra. If I union together a finite collection of finite sets, I get a finite set. So far, so good. If I union together a collection of sets whose complement is finite, union a bunch of sets together whose complement is finite, the complement of what results is even smaller than any particular one of the complements. So certainly we still get the finiteness of the complement. And then if I mix these together and union together some of these kinds and some of these kinds, I'll have a set that's got a complement that's finite still, similar argument. So this really is an algebra. It's not a sigma algebra because consider the natural numbers written as a union from, if you like, n equals 1 to infinity. Natural numbers. The natural numbers are an infinite set. Are the complements of the natural numbers finite? No. So neither the natural numbers nor the complement of the natural numbers is finite. So it's not in this set. But I can write the natural numbers as a union, a countable union of finite numbers. And in a sigma algebra, we've got a closure with respect to countable unions. Well, consider the union of all these singletons. Union from n equals 1 to infinity is implied. Each of these little highlighted sets is finite, but when I union a countable number of these things together from 1 to infinity, I get the natural numbers, and the natural numbers are not in that collection A. So each of these is, but the countable union is not. Okay, it's not a sigma algebra. It is an algebra, but it's not a sigma algebra. Next result relates to sigma algebras, and it's somewhat similar to what we had before. I've got a tiny bit of the proof in the notes. Really, the bulk of the proof of this is left as a homework exercise. It says, let C be a collection of subsets of a set X. In the intersection, calligraphy A, of all sigma algebras of subsets of X that contain C is itself a sigma algebra that contains C. Hey, we were intersecting algebras in that theorem we did before. Here, they're claiming if I intersect sigma algebras, then I get a sigma algebra. Moreover, this intersection of all those sigma algebras, is the smallest sigma algebra of subsets of X that contain C, in the sense that if B is a sigma algebra containing C, then calligraphy A is a subset of calligraphy B. It's the same thing we just did, except they've explicitly mentioned the intersections in this, and it involves sigma algebras instead of algebras. Observation before we look at the very humble comments related to the proof. So a collection of sets uniquely determines a sigma algebra. We'll call that the sigma algebra generated by the collection of sets. All right, I said we're interested in X equals the real numbers, and the subsets of X that we're interested in, the collection of sets we're interested in, it's open sets. We're interested in the sigma algebra generated by the collection of open sets of real numbers. So that's the plan. That's coming up next. Let's look at this proof super quick. There's not much in the notes concerning it, really. All right. First off, we know that an intersection of algebras is, again, an algebra. So we've got closure under finite unions, finite intersections, and complements. So if we want to show the sigma algebra part, we need to translate this from finite intersections and unions to countable intersections and unions, or only countable unions if you like, and then De Morgan. And then you need to deal with the smallest part. So you need to prove the sigma part and the smallest part. Proof goes very, very similar for a homework problem to what we did in the previous result. So you basically mimic what was in that theorem 1.1.A, wasn't? 1.4.a. There it is. Yeah, so it's quite similar to what was done up there. But I can borrow the algebra part. That's not enough because we've gone from algebras to sigma algebras in this claim. Okay, some little examples to motivate some things that will be in this sigma algebra. A countable union of closed sets of real numbers need not be closed. Yeah, it was a countable intersection. Actually, it was an arbitrary intersection of closed sets is closed. Here's an example where we take a bunch of closed intervals, let's say 0 plus 1 over n to 2 minus 1 over n. I put the 0 in there for emphasis. So on the left-hand endpoint, it's a little bit bigger than 0. On the right-hand endpoint, it's a little bit smaller than 2. Union that from n equals 1 to infinity, and that will produce the open interval from 0 to 2. You probably saw something like this in senior level analysis. So a union, even a countable union, of closed sets need not be closed. In fact, this closed set is these closed sets union to give an open set. It's certainly, most open sets are not closed. Not all of them. There's a couple of them that are both open and closed. But this is not a closed set on the right-hand side. In fact, a countable union of closed sets may be neither open nor closed. I can write the rational numbers as a countable union of closed sets. The rational numbers are countable. All right, so enumerate them. Denote the rational numbers as r sub I, where r is a natural number. You can do that. That's what countable means. And then union up those rational numbers. Union from I equals 1 to infinity, r sub I. Well, you took all of the rational numbers in that collection. So when I union this countable number of them up, we get the rationals. The rationals are neither open nor closed. And the rationals are everywhere. It's called a countable dense subset of the reals. But the rationals are countable. That's what's allowing us to pull this off. And the rationals are neither open nor closed. We're interested in describing, or at least naming, and I'd like to describe what the following collection of sets look like. It's not going to work very well. All the more I'm so proud that I know what an open set of real numbers looks like. Countable disjoint union of open intervals. Put that in your head. It should be left over from analysis at the senior level. But we know what open sets look like. Excellent. Open sets are important in analysis and in calculus because they give you wiggle room. But we're going to look at some more exotic sets, and I'd like to cleanly describe what they look like as well. But this is going to be a little awkward and a lot incomplete. So that's why I say I'd like to describe them. I'm not going to have a lot of success in describing all these sets. We can describe some of them, and we can give them all a name. So we're interested in describing the sets we get from countable unions, countable intersections, and complements of open sets. That collection of sets are called Borel sets. The collection, calligraphy B, of Borel sets is the smallest sigma algebra that contains all open sets of real numbers. All right, so it's the sigma algebra generated by the open sets of real numbers. Told you so. We're taking that set X that was the topic of conversation so far today and taking that to be the real numbers. And the collection, calligraphy C, of sets we're interested in is the all open sets, the collection of all open sets. And we're taking the sigma algebra generated by that collection. You know, such a thing exists by the theorem we just quoted. What I would love to do, since I can tell you what an open set of real numbers looks like, I'd like to tell you what a Borel set of real numbers looks like. And we're going to fail at that. I think a very reasonable question, isn't even touched on in the Royden and Fitzpatrick book. I think a reasonable question is, well, how many Borel sets are there? The thing we're going to do, we're going to measure subsets of the real numbers. We're not going to successfully measure all subsets of real numbers. We're going to measure some of them, but we're going to measure all the Borel sets. So we're interested in measuring the collection of Borel sets. I'm sorry, counting the number of Borel sets. I want to measure everything. It won't work. Our measure will be defined on the Borel sets. So a reasonable question is, how many Borel sets are there? That is, what's the cardinality of the sigma algebra of Borel sets? Got a reference for you. I don't have a proof. An introduction to measure and integration, which is what we're doing, an AMS book, I guess from about 20 years ago or so, claims that the cardinality of the Borel sets is the same as the cardinality of the real numbers, the cardinality of the continuum. If you like the continuum hypothesis, and most folks seem to, I'd say that's Aleph 1. So there's Aleph 1 Borel sets. Good news, we're going to be able to measure all of them. We're going to be able to describe what some of them look like. Actually, there's Aleph 1 open sets as well. But this is bad. Why is this bad? Let me restate that. There's only Aleph 1 Borel sets. Okay, I want to deal with all subsets of the real numbers, and I'm going to fail. We're going to include all Borel sets, but how many subsets of the real numbers are there? I'm asking you, what's the cardinality of the power set of the real numbers? Power set of the real numbers would have cardinality 2 to the C, was a notation we used. Buying the continuum hypothesis, or maybe it's a generalized version of the continuum hypothesis, then Aleph 2 would be the cardinality of the power set of the reals. So how many subsets of the reals are there? Aleph 2. How many Borel sets are there? Only Aleph 1. We're a whole level of infinity behind where we want to be. You know, that's kind of the story of analysis, because in senior level analysis, you had a real clean grasp of rational numbers. You know, everybody knows what a rational number is. It's describing them irrational numbers. It's tough. So how many real numbers are there? Well, there's Aleph 1. Yeah, but you only have, in some crude sense here, a clean grasp of Aleph 0 of them. In senior level analysis, you were talking about numbers and you were a level of infinity behind. Welcome to graduate analysis. Now we're talking about sets of real numbers and we're still a level of infinity behind. At least we, in some sense, got to Aleph 1. I'm saying, you know what an open set of real numbers looks like. Countable disjoint union of open intervals. I'm trying to describe some other sets. And even if I could describe all these Borel sets, geez, I'm still not describing many sets. I'm describing, if that, I would be describing Aleph 1 sets, and there's a total of Aleph 2 subsets of the real numbers out there. So we're not having a lot of luck describing what a set of real numbers looks like. This is the state of knowledge of mathematics, at this stage at least. So I want to say what Borel sets look like. And, well, we'll do what we can do, and we won't do what we can't do. Okay, we're going to define a couple of classes here. I want to go a little bit beyond what the book does. The book does include these two classes. A set which is a countable union of closed sets is called an F sigma set. A set which is a countable intersection of open sets is a G delta set. How did we start this section? What was the very first observation? Notice it deals with countable unions of closed and countable intersections of open. We started this section, back to page 1, by saying, recall, a countable union of open sets is open. Okay, well then what's a countable intersection of open sets? It need not be open. We can show that by example. What is a countable intersection of open sets? Well, that'd be G delta set, because that's what we called a G delta set. We know a countable intersection of closed sets is closed. what would a countable union of closed sets be? That would be F sigma, if I got my letters right. That would be an F sigma set, because that's what we define an F sigma set to be. Let me double check this. Countable unions of open sets are open. What are countable intersections of open sets? We gave those a name. That was G delta. When we changed this to intersection. I think I may have said it incorrectly recently. Countable union of closed sets would be called an F sigma set. So if I replace union with intersection and intersection with union, what kind of set do I get? Well, I'm saying I get one I can describe. Now the description is a little clunky. Back to the definition, I can tell you what an F sigma set looks like. So remember it like this. The sigma goes with union, like sigma and sum. We'll get some motivation linguistically here on the next page. Delta, maybe difference, intersection. More of that shortly. But can you tell me what an F sigma set looks like? Yeah, it's a countable union of closed sets. For what that's worth. Can you tell me what a closed set looks like? Well, its intersection is open, which means its complement is open, which means its complement is a countable disjoint union of open intervals. Can you tell me what a G delta set looks like? Yeah, it's a countable intersection of open sets. And I know what open sets look like. So a G delta set is a countable intersection of countable unions of disjoint open intervals. So this is countable intersections of countable disjoint unions of open intervals. So I can describe G delta sets in terms of open intervals. It's a clunky description, kind of second layer, but at least I got that. And same thing with the F sigma sets. I can describe F sigma sets in terms of closed sets. I might be a little bit better at describing the complement of an F sigma set than an F sigma set itself. Do you believe the complement of an F sigma set is a G delta set? That's true. I forget how much of this we're going to establish. But these come in complements, just as open and closed sets come in complements as a relationship. And here's why they're called that. I get this from Wikipedia. Wikipedia is not an entirely academic source, but says the F in F sigma comes from the French for closed, fermé, and sigma for somme, somme or union. So F sigma is a union of closed sets, countable gets in there somewhere. And G delta from the German, Gebiet for neighborhood, the idea of being open neighborhood. And delta, Durchschnitt for intersection. So intersections of open sets, countable getting in there somewhere. So that's the terminology everybody uses. I trust this is accurate from Wikipedia. It's odd that part of it's in French and the other part's in German. They naturally belong in the same conversations. I don't know the history behind that, but anyhow. Let's look at some examples of these F sigma and G delta sets and see some places where they pop up. They naturally arise in a handful of places. For us, we're just trying to describe what some Borel sets look like. And these are Borel sets for sure. They're, what was it? F sigma was countable unions of, let's look at G delta. G delta was countable intersections of open sets. Okay, open sets are in the collection of Borel sets because the Borel sets were the smallest sigma algebra containing the open sets. So it contains all open sets. And it's a sigma algebra, it's closed under countable intersections. Okay, so countable intersections of open sets are in the collection of Borel sets. That is, G delta sets are in the set of Borel sets. And a similar argument that F sigma sets are in the Borel sets as well. So we've described some of the Borel sets, the F sigma sets, and the G delta sets. Countable sets are F sigma. just like we wrote the natural numbers. Actually, we wrote the rational numbers as a union of a bunch of closed sets, the singletons that make up the rational numbers. Yeah, every countable set can be written as a union of the singletons that make it up. Single points, singletons, a set of cardinality 1 containing a real number. That's a closed set. Its complement's open, eh? So we've got countable unions of these closed singletons that make up a countable set. Okay, so countable sets are F sigma. Of course, closed sets are F sigma. Countable union of closed sets. One union of one closed set. So there you go. Certainly closed sets are F sigma. A countable collection of countable sets is itself countable. Got that? Countable collection of countable sets is countable. We stated this, I think, in the background material, the very first stuff, that a countable union of countable sets is countable. It's related to that. So if we take a countable union of F sigma sets, that's again an F sigma set. The collection F sigma is closed under countable unions. Yeah, it might not be closed under complements, though. I'm not saying the F sigma sets form a sigma algebra. The F sigma sets are some subset of the Borel sets, a subset of the Borel sets that's closed under countable unions. I bet you the G delta sets are closed under countable intersections as well. That's true. Every open interval is an F sigma set. So F sigma was expressed in terms of countable unions of closed sets. An example of an F sigma set is the open interval from A to B. Okay, it's based on closed sets, but I can take the open interval from A to B and write it as a countable union. We did something like this upstairs. Write it as a union from 1 to infinity of A plus 1 over n to B minus 1 over n. Or n sufficiently large, so these are actually non-empty. Let's see, this left-hand endpoint is a little bit bigger than A. The right-hand endpoint's a little bit less than A. Union up, 1 to infinity. That 1 over n goes to 0. This approaches A, this approaches B. Union them all up. You get the open interval from A to B. Of course, you never get the endpoints out because this 1 over n never is actually 0 for any n, 1 to infinity. If we took A and B to be infinity, then we'd have to revise this a little bit. But you can also write the whole real line as a union of closed intervals. I just take a negative n to n and union that from 1 to infinity as closed sets, and it'll squeeze out and include all real numbers. So, hey, all open intervals, in fact, are examples of F sigma sets. Yeah, they're G delta sets as well. Remember, the G delta sets included all open sets and all countable intersections of open sets. So here's some stuff that's in both collections. All open intervals are in F sigma. All closed intervals are in G delta as well. So there's some overlap between F sigma and G delta. Oh, when they have you, I guess, establish some of this as some of the exercises. A claim, the complement of an F sigma set is a G delta set, and conversely, you buy that, piece of cake. Whose law are you going to use to prove that? De Morgan. What's a F sigma set? Sigma union F closed. It's a countable union of closed sets. Okay, if I take a complement of that, we'll get a countable intersection of the complements of those closed sets. The complements of closed sets are open. So by taking a complement of one of these, union of closed sets, we get an intersection of open sets, and countable, this underlying all this, we get a G delta set. So De Morgan gives you this relationship. One place these arise, real outside chance you might have seen this in senior level analysis. I don't know, we got close to it when we were talking oscillation in the Riemann-Lebesgue handout. There was a comment made that was relevant to this. I think maybe the word G delta or F sigma was even used. I think we were talking about the points of discontinuity of a function and said that was F sigma, I think is how we had dealt with it. Young's theorem says, let f be a real valued function defined on all the reals. The set of points at which f is continuous is a G delta set. All right, well then the set of discontinuities must be an F sigma set because these are complements of each other. And that function's either continuous or discontinuous. So set of points of continuity is a G delta set, or if you like, set of points of discontinuity is an F sigma set. We observed something along those lines when we were dealing with the oscillation of a function in the Riemann-Lebesgue theorem. The converse of Young's theorem also holds in the following sense. I give you a couple of references on this. This is not from the Royden book. If we take any set A that's a G delta set, then there exists a function f defined on all the reals such that f is continuous at every point of A and discontinuous on the complement of A. So there exists a function that's continuous on set A and discontinuous elsewhere. Its set of points of continuity is this set A. So up there they say the set of points of where the function is continuous is a G delta set for a given function. Down here they say for a given G delta set, I can find a function that's continuous only on set A and discontinuous everywhere else. Okay, in my quest to describe sets of real numbers, I'm going to go a little bit nuts on this to show you in some sense how little you know. Depressing. For delta, with delta representing intersections and sigma representing unions, we could construct, for example, a countable intersection of F sigma sets. We said something upstairs that a countable union of F sigma sets was again F sigma. It was that countable union of countable things is countable deal. Well, here we're not doing unions, we're doing intersections. Just like when we started out with the very first observation, say a countable union of open sets is open, and ask the question, well, what happens if you take a countable intersection? Well, then you get what we call a G delta set. And if I took countable intersections of G delta sets, I'd just get more G delta sets, as we would if we took countable let me get it straight here. If we took countable unions of F sigma sets, we just get more F sigma sets. So what if you flop from countable intersections to countable unions? What if we took a countable intersection of F sigma sets or a countable union of G delta sets? I wouldn't necessarily get an F sigma or G delta set respectively. What would you get? Well, I get a countable intersection of F sigma sets. Let's call such a thing an F sigma delta set. Delta, because we're talking intersection, and the little delta is just tacked on as a second subscript. Hey, what if we took a countable intersection of these, we just get more of these. What if we took a countable union of the F sigma delta sets? Why, then we get an F sigma delta sigma set. And then we could take countable intersections of those to get F sigma delta sets, and so forth. And we could similarly manipulate the open sets, the G delta sets, G delta sigma delta, and so forth. Can you tell me what a G delta sigma delta set looks like? In the following way, I can. Okay, delta means intersection, sigma means union, and G means open. The last level is either going to be of open sets, or I can describe those open sets as countable unions of disjoint open intervals. Then I can take it all the way back to intervals. All right. A G delta sigma delta set is a countable intersection of a countable union of a countable intersection of open sets. An F sigma delta sigma set is a countable union of countable intersections of countable unions of closed sets. Let's do this one again. But let's describe open sets in terms of what they are. So a G delta sigma delta set is a countable intersection of countable unions of countable intersections of countable disjoint unions of open intervals. The disjointness word we could toss if you like, and then it's more consistent with the other stuff. So we can describe these sets I've highlighted here, that collection of sets, we can describe in terms of open intervals. For what it's worth. Granted, it's a clunky description, but that's what we've got. Okay. So we could describe these classes as sets, F, sigma delta, sigma delta, sigma delta, sigma delta, and they ultimately boil down to countable unions and countable intersections of open sets, or countable unions and countable intersections and countable whatever of closed sets. Got some bad news for you. If you were to do all these F sigma delta things and all these G delta sigma things, you still don't get every Borel set. Not every Borel set belongs to one of these alternating sigma delta classes. Well, that's the ones I can describe, and boy, is it a clunky description. But that doesn't even cover describing all the Borel sets. And remember, there ain't many Borel sets in terms of how many subsets of the real numbers there are. So you see now why I'm so proud that I know what an open set looks like, because I'm so grasping at straws to describe these other sets and getting a little progress done, but in a cardinality sense, not much progress at all. We didn't even get the Borel sets described, and there ain't even many of those. Welcome to analysis. One final observation. This is problem 57 from chapter 1. I stated it as a theorem. Gives you a reason outside of this measure theory stuff that you might be attracted to a particular class of Borel sets. Let f sub n be a sequence of continuous functions defined on the reals. Then the set of points x at which the sequence f sub n converges to a real number is the intersection of a countable collection of f sigma sets. Intersection, countable collection of f sigma set. Hey, that's an f sigma delta set. So sequence of continuous functions, the collection of points on which those converge is an f sigma delta set. So there's a place I can describe f sigma delta sets as naturally arising in the setting of the set of points at which a sequence of functions, a sequence of continuous functions converges is an f sigma delta set. So, well, there's just something that talks f sigma delta from a set that's not really measure theoretic. I guess you might see something like this. You consider sequences of functions, at least power series, and partial sums of power series as a sequence of functions. You see that in calculus too. And maybe in some applied classes, you might see this kind of thing. But I doubt you'd see this kind of thing in an applied class. But that gives a motivation for this F sigma delta stuff, independent of just Borel sets and trying to describe what Borel sets look like. So there's some structures that we're interested in. We're definitely interested in sigma algebras. I got some good news for you. I'm done with this sigma delta stuff for the most part. These are Borel sets. These will all be measurable sets, and there'll be a bunch of measurable sets. Some good news, there's a lot of measurable sets. There's as many measurable sets as there are subsets of the real numbers. But you can't measure all subsets of the real numbers. There are non-measurable sets. There's a lot of those too. There's infinitely many of those, and it's a bad kind of infinity. So we'll explore this in more detail, but this gets you started on an idea of sigma algebras. The Lebesgue measure will be defined on a sigma algebra of sets. And one of our big results and one of the titles of one of the upcoming sections is the sigma algebra of measurable sets, or Lebesgue measurable sets. So this was necessary background. From here on out, we'll get into the measure theory per se, and we'll start chapter 2 in the next lecture. Have a nice day.